Hello, so welcome to my presentation on the Flood Hydrograph. I'd like you to do here is to make a copy of this Flood Hydrograph that's in front of you into the space in your booklet. Don't worry about what you're copying, just copy it all down, write everything down, draw the lines. So if you pause the video now and do that. So hopefully then you've got a nice copy of your own of a flood hydrograph, and we're going to have a little look through the different bits and pieces and what it means. So first of all, we just want to talk about a few key terms here. First of all, velocity. So hopefully you already know this, but just a sort of reminder of what velocity means. So velocity is speed, and it's the speed of the water travelling in the river channel. Okay, so that's what we're referring to when we talk about velocity here. The second is discharge, river discharge, and this is the volume of water flowing through a channel, and it's measured in cubic meters per second, which is cumex for short. Okay, so it's the amount of water flowing through the river. So if you're going to calculate a discharge of a river, you need three things. You need to know the width of the river, the depth of the river, and you need to know the velocity, so the speed the water is travelling at. Once you've got those three things, then you can calculate the discharge, the cumex. So you do your width times your depth to give you the area, and then you times that by the speed, the velocity, and that would then give you the discharge. Just added to that, going back to your storm hydrograph, it says peak discharge. There's a point where it marks peak discharge. That is the highest level of discharge from a river following a rain event. So if we go back to our storm hydrograph now, or flood hydrograph, we can just talk through a few bits and pieces on here. So if we look on the left-hand side, it has two scales. So you can see there's the one sort of written at the bottom, which says rainfall in millimeters. And then on the other side of that line, it's a different scale, and that from 10 to 40, and that is the river discharge in cumex. Okay, so cubic meters of water per second. If we look along the bottom, I know it's slightly cut off here, but hopefully you've written it on. It says time, okay? And then there's an arrow going along there. Obviously, if this was for an actual storm event, we would know, we'd be able to put the number of hours and so on down there. But because it's a model, then we just put time on there. So the first thing to have a look at then is the bar. So there's a little bar graph there, and that refers to the rainfall in millimeters. So that is the rainfall from our storm event, because this is a graph of a specific event, a specific rainfall period. So we can see there it starts off with no rain, then there's a small amount, it grows a little bit, and then there's the largest amount when the rain is at its heaviest. It then falls away slowly, so there's still some quite heavy rain for a while, and then the rain event finishes, stops. So that there just shows us what happened in this rain event. And we can see there that we've got an arrow pointing to peak rainfall, which is the highest amount of rainfall. What we then look at happening is that green sort of line, okay, which starts off next to and on the red dashed line, but then it starts to rise away from that line, and that is the discharge. Okay, so that line there is showing us how much the river it is discharging. So it's at approximately 5 cumex when it first starts. So the river is normally at about 5 cumex. And we can see then that by the end of the rainfall event, it has risen to about 10 cumex. So it's gone up because it's raining and water's going into the river and so on and so forth. Then what we see is that it then starts to increase, and that the amount of discharge is increasing quite rapidly. And you can see that that's labelled there with the rising limb. So that's when the water that's fallen in this rain event all starts to get into the river, and it starts to then increase the level of water in the river, so the depth and the speed of the water flowing is going to increase. and that's our rising limb. And we can see there that the river discharge gets up to about 35 cumex, and we can see that's where we've got it marked. There's an arrow pointing to it, to the peak discharge. Okay. What then happens after the peak discharge is that there's still a lot of water in the river, but it is now starting to decline, and that is then labelled as the falling limb. Okay, so it's as the water goes away, that's called the falling limb. And eventually then the discharge in the river goes right the way back down to kind of where it started at the beginning. Okay, and that's sort of our basic of the flood hydrograph. That's showing what's happening. There were a couple of other little features on there. So there's the base flow, and that's basically the sort of the normal river. So what the river would normally do without this big rainfall event. That's what you're looking at there with base flow. And then you've got then the section above that dotted line of base flow, which is the storm flow. So basically all of that is all of the extra water that this river has dealt with and got rid of and passed through it as a result of that rainfall event marked on here. There's one more thing, and it's perhaps the most important thing, and that is the lag time. And I'll mention it here, but we're going to talk about it in more detail. But we can see here the lag time is that difference. So it's a measured difference between when the peak rainfall occurred and when the peak discharge occurred. So measured in time, linking to the bottom, to the x-axis, and it's the length of time it takes for the peak rainfall and to become the peak discharge. Okay, so that there is our flood hydrograph. Hopefully you've got a bit of a better understanding of what you've drawn now, and we'll look at a few details on that now. Before we do that, if you'd like to have a little look at this YouTube clip, I've put it in the work, so you can clip and have a little watch of this. It's quite nice just to make sure you do understand exactly what we're in the real world, what we're referring to with this sort of hydrograph and that line. So I suggest you sort of maybe stop this now, have a look at that clip, and then come back to here afterwards. Okay, so I said we'd talk some more about lag time because it's so important, and as I've said here, it's perhaps the most important part of the flood hydrograph. And it's the amount of time it takes the peak rainfall to reach the river, to become the peak discharge. And the longer the lag time is, the less likely a river is to flood, which is why it's so important. So if you don't want river discharge to be higher than the river can take, because obviously the river can only manage a certain amount of discharge before it goes out of the river and starts flooding, then if you extend the lag time, you will be able to bring down that peak. Now, it's interesting that this concept you might have seen and heard about quite recently with this concept of flatten the curve with the COVID-19 response. It's exactly the same idea. We've tried to bring down the peak, bring down the top by extending the amount of time that the event is happening, and that's been done to prevent NHS services from becoming overrun, having too many people needing hospital care. And that essentially is to prevent the service from becoming flooded. So it's exactly the same principle, even though it's in a very different context. So the lag time, if we can extend it, the peak discharge will go down, so our river is therefore much less likely to flood. Okay, so we're going to have a little look now at a range of different factors that would affect flood risk, and we're going to look at some hydrographs alongside them to sort of make sure that we understand why these different things cause flood risks and the difference between them, and also just get a better understanding of what a flood hydrograph looks like. So the first one is, how does precipitation affect flood risk? Well, it's very straightforward really, isn't it? The more rain there is, the more water there is going to be in the river channel, therefore it's more likely to flood. Not too tricky to work that one out. Also, alongside that, if there's been a lot of rain, and particularly if there's been rain for a long period of time, the ground itself will be saturated, will be full of water, and so any new rain that falls on top of the ground can't soak into it, and so it flows across the top and reaches the river more quickly. So a long period of rain is also a flood risk. So once it's been raining for a long period of time, more likely to flood, or if you suddenly get a very heavy rainfall, it's more likely to flood. And rain and precipitation is generally the main cause of river flooding, but we've got some other factors we're going to have a look at now which actually affect the risk of it being likely to flood. Okay, so let's have a look at that. So first of all is geology. So geology is rock type. So we've got two broad categories of rock type: impermeable rocks, which are ones that do not allow water to go through, and permeable, which do allow water to go through them. So we've got two different types. So first of all, if we look at permeable rocks, such as limestone, which allows water to kind of infiltrate into the rock structure itself, um, compared to an impermeable rock such as granite, which doesn't allow water to infiltrate into it. So, as we can see then on our graph then, if the rock is impermeable, the water is going to sit on top of the land and then flow more quickly into the river. So the lag time is going to be much shorter. Look at where the peak discharge is. Okay, it's much closer to the beginning, to the start of the graph, and it's also much higher. So the higher peak, so the peak is higher and the lag time is shorter. So our river here is much more likely to flood in areas of impermeable rock. If instead it's permeable rock, then the water is going to be able to infiltrate in, some of it will, and therefore the lag time, as we can see, is much longer. So that distance between when the rain occurred, which is at the beginning of the graph here, and the peak is, well, it's about twice the distance, maybe not quite twice, but it's certainly further. And it's much lower, isn't it? The amount of water in the river at any one time passing through it is considerably lower. So therefore, in areas of permeable rock, you're much less likely to get a flood. So at the bottom there, yeah, if it's permeable, we've got longer and lower are the two missing words there. Okay. Next then is relief. So relief, and we've used this word before, is referring to how steep the slopes are when they're near to a river. Okay, so how steep are the slopes, the relief of the land. So where the slopes are very steep, the water will rush into the river quite quickly. Okay, and we can see there with the blue line, the solid blue line, when it's steep, the peak discharge is higher and the lag time is also shorter than when we have much more gentle slopes where the water will be able to move more slowly. It's more likely to soak into the ground, so it's just going to have that longer lag time, and therefore the peak discharge, the highest point, is much lower and later. Okay, so much less likely to flood in area. The river is much less likely to flood in areas of gentle slopes. Okay, so next one is our land use. So if there are lots of trees, for example, and that's one of the key things we can do to prevent flooding actually, is planting trees, then more water is going to be stored on the leaves and in the tree, and it will take it much longer to reach the river. So as the water falls, it gets trapped on the leaves, sits there for a while, and then drips off slowly. And so therefore the water doesn't reach the ground for less time, so therefore it takes much longer for it to get to the river. So this then is going to extend that lag time, as we can see there with the blue, the green dotted line, dashed line, that the lag time is longer, and is also lower, so a much lower peak discharge. So where you've got lots of trees, you're going to be less likely to get flooding. If the land use is urban, there's going to be a lot of impermeable surfaces, so concrete, for example, okay, and where there are drains put in place. That's a really quick way of getting water from into a river. So it flows incredibly quickly through the drains, sort of very quickly to the river. So that then, if you've got land without sort of forest, without trees, or indeed even worse, if it's an urban area, the peak discharge is going to be very high, as you can see there, much higher, but also the lag time is incredibly short, and those two things are obviously linked. So that short lag time equals high peak discharge, so therefore far more likely to flood in an area, an urban area, or an area without very much vegetation on the ground. So we've got there the result. So this results in a longer lag time and lower peak discharge. And at the bottom there, this makes peak discharge higher and lag time shorter. Okay.